tell Matthew to start the YouTube. Yeah, it's starting now. You can introduce
All right.
tech.
Yeah, thank you, Oscar. Welcome, everyone. Thank you very much for joining us for a CAP talk tonight. This time we are incredibly pleased to host a very special one. Just to remind you, this academic year, our events have been kindly sponsored by Seamless, Riverlane, TTP, TPP, Define, Jane Street, and CGG. By the way, on the 31st of October, there will be a careers conference, which are invited to participate in. You might find more details on our Facebook page. As for the talk, if you have any questions, please feel free to post them on the YouTube chat. There will be a Q&A session afterwards. Now, I'm greatly honored to introduce you our very distinguished speaker, Professor Duncan Haldane. Professor Duncan Haldane is currently the Sherman Fairchild University Professor of Physics at Princeton University and the Distinguished Visiting Research Chair at Perimeter Institute for Theoretical Physics. He is a co-recipient of the 2016 Nobel Prize in Physics, along with David Dulles and Michael Kosterlitz. The prize was awarded for theoretical discoveries of topological phase transitions and topological phases of matter. Professor Haldane studied at the University of Cambridge, where he received his PhD in 1978. His supervisor was the future Nobel laureate, Professor Philip Anderson. Professor Haldane has worked at Institut Langevin in Grenoble, France, the University of Southern California, Los Angeles, Bell Laboratories, Murray Hill, New Jersey, the University of California, San Diego, and since 1990 at Princeton University, New Jersey. Professor Haldane is known for a wide variety of fundamental contributions to condensed matter physics, including the theory of Luttinger liquids, the theory of one-dimensional spin chains, the theory of fractional quantum Hall effect, exclusion statistics, entanglement spectra, and much more. He has been developing a new geometric description of the fractional quantum Hall effect that introduces the shape of the composite boson described by a unimodular, which means determinant one, spatial metric tensor field as the fundamental collective degree of freedom of fractional quantum Hall effect state. Professor Haldane, the stage is yours.
Thank you. Well, it's great to be back, at least virtually, at my alma mater, Cambridge, where I was in the theory of condensed matter group, TCM. And today I'm going to tell you about some of my work and the ideas of topologically protected quantum computing, which is a kind of dream that a lot of people in my field are kind of pursuing at the moment. So the modern laws of quantum mechanics are really established a long time ago, period about 190 years, I guess, almost 100. And the laws of quantum mechanics haven't changed, basically, since they were formulated correctly in this period. On the other hand, just because we know the basic laws doesn't mean we know all that they allow to happen. It took a long time to work out, to go from Maxwell's equations to finding out what you could do with them. And in fact, there's the old story that Gladstone had apparently had a meeting with Maxwell, and he said, these are very nice, all this stuff is very nice, but what's it good for? And Maxwell's response supposedly was, I cannot say, but one day, sir, you may tax it. And of course, electromagnetism is still an evolving subject. You know, in recent years, all kinds of new things like photonic crystals, and in fact, topological photonic crystals are a new thing. And of course, the whole mixing of quantum mechanics with electromagnetism in lasers is still an ongoing area where all kinds of things are happening. So what about quantum mechanics? Well, you know, we had the basic laws of quantum mechanics for a long time, but really the new ideas which people are excited about is so-called quantum information theory. And starting around 1980 or so, at the same time, we had new insights into quantum mechanics, which started to reveal these new topological quantum states of matter. And somehow in recent years, we've put together these two ideas of exotic topological quantum states and quantum information theory. So, of course, Feynman, I guess, first started thinking about a quantum computer, or started thinking about what would happen when the computer architecture size got down to the atomic scale where you couldn't ignore quantum mechanics. And he started thinking about this basically as a way of using a quantum computer to simulate quantum mechanics to discover things about quantum matter. But these ideas have grown, and there's a lot of hype these days, but some people think it's the second quantum revolution, that after the first quantum revolution of the 1930s, we've suddenly come to a new way of looking at things. And I think it's true that our understanding and the practical use of quantum mechanics is really going to evolve dramatically in the next 10 to 20 years. So the basic thing is to control quantum states in a very clean way, very exquisite control of them, rather than just bashing a system, doing some measurement that destroys the quantum state, and look at the pieces that come out. But anyway. So anyway, the key message of this talk is probably that as we understand quantum mechanics better, we're going to have new possibilities seem to be emerging for materials of the future and possible technologies. And this new understanding really came about through surprise discoveries. The best discoveries are things that no one is looking for, right? That you don't, no one imagines them, that they're out there. And so most of the really unexpected things, which are surprising, come about through some combination of luck to actually stumble across them. So what is quantum information? Well, classical information is stored in a bit, a kind of switch, which is either on or off, basically. So the two basic units in your today's computer are just 1 and 0, on and off. And those can be simulated, or those can be created by little magnetic domain that's pointing one way for up and the other way for down, for example. And you can make that out of a large group of little atomic spins, which all want to line up parallel to each other, as in a ferromagnet. And up or down, large numbers of objects in the same state, they behave classically. But the quantum information is stored in a state of a single spin called a qubit. And to read it, you have to make a measurement with a choice of a measurement axis. So the qubit, the spin, if you measure its projection onto any axis, the spin half object, the basic qubit, is either pointing up or down, but it could be point up or down, could be north or south, or it could be east or west, right? And in fact, the quantum information of a single qubit can be represented as what's called the Bloch sphere, the direction of a spin pointing in any particular direction on the sphere, and it can be represented as some complex numbers. And any qubit system is that with two states is actually just equivalent to a single spin quantum mechanically. And you can see, rather than just up or down, there's a much more richer kind of information contained on the Bloch sphere. So anyway, the central theme in this new approach is to quantum physics is this property called entanglement. Right? 10, 20 years ago, entanglement was something that philosophers of quantum mechanics worried about. It was introduced as part of paradoxes of quantum mechanics. But now it's really recognized as from being a peripheral kind of thing that philosophers argue about. It's now become really recognized as a central property of quantum mechanics, and it's currently viewed in some way as the fuel which can drive future quantum information processes. And in fact, Einstein first pointed out entanglement as something so ridiculously predicted by quantum mechanics that he thought for a long time that quantum mechanics couldn't possibly be the correct description of the universe. So, of course, Einstein actually got his Nobel Prize in 1919, not for his theory of relativity, which was the big thing at the time, but actually for his early contribution to quantum mechanics in the photoelectric effect. But anyway, by 1935 or so, Einstein had rejected the quantum theory, and he identified a key property predicted by quantum theory he felt had to be wrong, which was, he called it spooky action at a distance, or spukhafte Fernwirkung in German. But Schroedinger came up with a less pejorative name and came up with a name that's been translated in English to entanglement, Entwicklung. I guess in all languages seem to have adopted a separate word for entanglement. It's quite interesting. Entanglement is not each language seems to have adopted a different word for this quantum process. So one of the fundamental properties of quantum mechanics is, of course, the Pauli exclusion principle, which says that two electrons, which are fermions, cannot be in the same state. So, of course, in addition to the position, the state of an electron has this extra internal degree of freedom, the spin, which is sort of analogous to the direction of a spinning top. And it's the chemical bond, of course, is actually, which holds all the matter we're made of together, is made of two electrons with exactly opposite directions of spin, which allows them basically to occupy the same region of space in between the two atoms that they join to with the chemical bond. So the chemical bond is actually the maximally entangled state of the two electrons. And it can be represented in terms of, because if one electron is pointing in one direction, the other one is always pointing in the other direction. Now, we usually represent that as up-down, and up-down minus down-up, because the wave function or the state of the pair of electrons is odd under swapping the two electrons around. But it could equally be backward, left, right, and right, left. It doesn't matter what direction the first arrow is pointing in. The second arrow will always be in the opposite direction. And that's so the chemical bond is the poster child of entanglement. So what Einstein worried about in 1935 was he worried about if I took an entangled pair of electrons from a chemical bond and stretched them and pulled them so they still remained entangled when they had a large distance between them. He felt that if you now measure the direction of the spin of one electron, the quantum mechanics immediately predicts that anyone who measures the spin of the second electron will always find it pointing in the opposite direction to the way that the first measurement said it was. Of course, you had to pick some direction, some axis to do that measurement. But the basic the worrying problem to Einstein was somehow that this seemed to contradict his relativity principle that says nothing can travel faster than the speed of light. So if you measure one, does that mean, and the other one is, once you've measured the left electron spin, the right electron spin is always in the opposite direction. Does that mean that the information about the measurement had somehow traveled instantaneously? And actually, when you look at it more carefully, no, you can't use this to transmit information, because it's a bit like you take a laser pointer and point it on the surface of the moon. You could make a spot that moves across the surface of the moon faster than the speed of light, moves tangentially on the surface, but you can't, someone at one place can't use that on the moon, can't use that to transmit any information to someone on the other side, another place on the moon. So no information can be transmitted, even though it seems like this information seems to be instantaneously commuted. Anyway, so Einstein, this gave rise to this Einstein-Podolsky-Rosen paradox, and it actually made the headline of the New York Times when that day someone, I guess Podolsky, went to the papers and said Einstein has demolished quantum mechanics or something like that. And I guess, no country had been invaded that day or anything, so it was a kind of a weak news day. But anyway, it made the front page headlines. Einstein was actually furious with Podolsky about it. Apparently, he didn't speak to him again. He felt that physicists shouldn't be washing their dirty linen in the public. But anyway. So the question was, before the measurement is made, is the system up, down, minus down, up? Is it at the same time until the measurement happened, or was it already split into one way or the other way when the two particles were started to be separated? So Bowman and Bell really made a deeper analysis of the thing long after Einstein's death. Einstein felt that eventually this thing would be measured and it would demolish quantum mechanics. But of course, by 1982, it was possible to do such measurements. And Alain Aspect, the French physicist, seems to be often credited with the experiment that demonstrated Bell's paradox and showed that the quantum theory was basically 100% correct. So no one's career has ever been made by betting against quantum mechanics. But the issue is the size of the chemical bond is very small. It's about 0.1 nanometers, and its stability is protected by a kind of sizable energy gap needed to break it. But when I stretch this object over large distances, it becomes very fragile against decoherence, which means interacting. Each electron has a chance to interact with other electrons in its local environment and become entangled with them. So, but on the other hand, photons, particles of light, can remain entangled over much larger distances, because after all, light from the Big Bang, or not from the Big Bang, but from when the atoms formed at the early stages of the universe, light is still coming after billions of years. So photons manage to travel large distances without interacting with their environment. And indeed, EPR, the Einstein-Podolsky-Rosen now, in terms of photon pairs with polarization replacing spin, is now a standard thing. And it started off by using optical fibers to have entangled photons separated by the width of Lake Geneva, but now it's extended to having them entanglements between ground and orbit, satellites in orbit and things. So you can really produce photons in entangled states which are separated by very large distances. So around about 1980, condensed matter physicists thought they had a basic understanding of electronic and magnetic materials. Of course, every time people start to say, well, we kind of almost know everything, that's basically when something's going to happen to shake things up, because we're never going to know almost everything, right? We're always going to find out that our understanding is incomplete. And so around that time, there were kind of two examples of weird properties that didn't fit into the standard picture emerged. They didn't seem to have any connection at the time, but now we know they're both examples of a new kind of condensed matter in which quantum entanglement plays a key role as opposed to a peripheral role. So one of them was the integer quantum Hall effect by found in Grenoble by Klaus von Klitzing. Again, in an unexpected experiment, it was something that no one expected, including him. But then he discovered that his measurement on his digital meter or something came up of a voltage which every time he did the experiment came up to the same number up to 6 or 7 significant figures, which is ridiculous, right? Usually experiments on some lump of matter are they'll give you some number plus or minus something else, but they won't give you a very accurate value. And it turns out there was a lot of accident in the way the experiment was set up, which allowed this thing to emerge. Also, there was something else, which I'll talk about briefly, which was my own work, which is I found something strange in magnetism. But in the meantime, many, many more kinds of this topological quantum matter have been found in the last decade or so. And it's kind of like these two things were like the little tips of the iceberg, apparently two different tips of one single iceberg floating around. So as I say, these unexpected properties of the topological quantum matter led to a lot of excitement among condensed matter physicists in the last decade, and the growing excitement, which is mainly due to actual experimental verification of things in the last decade or so, led to this Nobel Prize. So it took a long time for of course, von Klitzing's work was so obviously important, it got a much earlier Nobel Prize, and of course it's got a tremendous implications for the metric system, for example. So what really has made this stuff very topical is that it's been proposed that you can use some topological types of quantum matter for topologically protected quantum computing, which could in principle avoid this decoherence problem that plagues spatially separated entanglement, which is local. So what's topological matter? So topological matter differs from ordinary matter because it's got some properties which actually can, in general, some kind of entanglement properties that can be described by whole numbers, like -1 or so, right? An integer. So the basic issue is if the state of matter is characterized by two states of matter are characterized by different whole numbers, they can't continuously or smoothly change into one another. There has to be a jump. You can't go continuously from 0 to -2, for example. And so if there's a region of interesting matter classified as -2, surrounded by boring normal matter classified here as 0, there has to be something interesting at the boundary between the two things. So the initial types of topological matter, the simplest kinds, you didn't see anything special in the middle of them. You didn't see that the -2 was particularly different from the 0. But what was found and had been missed for many years, there had to be something very interesting happening on the boundary between the two, and the boundary can never go away. So this property of that they can't change, the properties can't change continuously, means that there's a robustness in topological properties, right? You know, a current technology, the silicon chip, they have to be made in these absolutely ultra clean chip factories where the workers are dressed in these very elaborate kind of spacesuits. They're not designed to protect the workers from the nasty chemicals that they might be using in the process. They're designed to protect the silicon wafers they're producing from any bits of hair or dust or something that come off the workers, right? So you require ultra clean systems, and one little speck of dust on a silicon chip means it has to be basically rejected and lost. But the topological systems really in principle, have a robustness which makes it hopeful that they can be used for something like the quantum computing system. So the classic example in mathematics of topology is the classification of closed surfaces by what's called a genus, or the number of holes in the surface, right? So we can take a shape such as a sphere, which could be a football or a rugby ball with 0 holes, and we can squeeze the football and make it look like a rugby ball, but I need a really violent event to turn it into something like a swimming ring or a donut with a hole in the middle. And of course, that goes down to the fact that holes are topological quantities. There's no such thing as 0.3 of a hole. You either have a hole or you don't have a hole, and something had to happen in between the two, the cases of hole and no hole. This goes back to a great mathematical discovery by Gauss. So Gauss was one of the greatest mathematicians of all time. But out of all his discoveries, he felt this one was the most surprising to him. It's called the Gauss-Bonnet theorem, I guess, because he didn't write it up properly, and Bonnet wrote up the proper details of the proof later. But what Gauss discovered was a simple high school fact, right? You take the surface area of the sphere. The curvature of the sphere is actually the Gaussian curvature is the product of the two principal radii of curvature at any point of a surface, and a sphere is uniform, so the Gaussian curvature is 1 over r squared. And what Gauss found was if you integrate the Gaussian curvature over the surface, well, if it's over a sphere, you get 4 pi, because 4 pi r squared times 1 over r squared is 4 pi, right? But he discovered that was true not just for the sphere, but if I deformed it into a rugby ball or even a banana, you still got exactly 4 pi when you integrated the much more complicated Gaussian curvature function over the surface. However, the amazing thing is that the actual number is 4 pi times 1 minus the genus. So this leads to the thing that people always show when they discuss topology, right? The experimentalist who's been working on topological insulators, he can't wait to show the YouTube movie of a bagel turning continuously into a coffee cup and backwards, right? So if I take the ball, the curvature of on the ball is everywhere positive and integrates to 4 pi. If I look more closely at the bagel, I can see the outer part of the bagel has positive curvature. Both radii of curvature are pointing inwards. But if I look at the part near the inside ring of the thing, one of the radii of curvature is pointing to the center of the is pointing outside the surface to the center of the ring, and the second radius of curvature is pointing to a circle which goes down the middle of the bagel. So the product of the two is negative in that region, and that's why I get a balance of positive curvature on the outside and negative curvature on the inside, which exactly balances to 0 for the coffee cup. Then there's this thing which was being used, which people know about as a loving cup. And the loving cup is topologically equivalent to what was at the Nobel press conference was called the Swedish pretzel, was called a pretzel. In fact, it's not a pretzel because the pretzel has 3 holes in it. So this is a Swedish pretzel, which is actually a Santa Lucia bun, which they eat, except usually when they bake it, the holes sort of get filled in. So then, of course, we can go to this other object. This is, each time I make an extra hole, the value goes down by -4 pi. So I make a second hole, and I get this object, the regular pretzel, which you get 8 pi by integrating on it. And of course, here is this object. I actually don't know what this thing is called. I've heard it, some people have suggested it should be called a California loving cup, but anyway. So there you go. So we have this nice topology of surfaces. What's that got to do with quantum mechanics? Well, in 1944, the Chinese mathematician Chen, I guess he was at Harvard at the time, he generalized the Gauss-Bonnet theorem about regular surfaces in 3-dimensional space to a much more abstract algebraic form. He actually generalized it to even-dimensional surfaces. And the curvature in even-dimensional manifolds, which are continuous spaces you can walk around in, and they had to have an even dimension, and you ended up getting the Euler characteristic out of the thing. So of course, the mathematicians like to find the full generality of things. So the Gauss-Bonnet formula got turned in from a formula about donuts and coffee cups in real space to a much more abstract formula of curvatures on manifolds, on continuous manifolds in abstract space. And indeed, the mathematicians are sort of ageist. They don't have a Nobel Prize. The rumor is that it's because Nobel's wife had an affair with a mathematician, so he was prejudiced against mathematicians and didn't include them in his list. And they have a prize for young mathematicians, but if they're over 40, they don't qualify. So they've invented some medals for lifetime achievement there, and one of them is the Chern medal, and it's got the Gauss-Bonnet-Chern formula engraved on the back of the medal. It's really a remarkably simple formula. But okay. So where does this come up? How does this relate to quantum mechanics? In recent years, we've realized that the quantum condensed matter can have unexpected properties which are associated with the kind of long-range quantum entanglement. So what's entanglement really mean in this context? If I have an object here, if I make a measurement in this part of the system, does it affect a measurement that's made in the other half of the system? Okay. So for trivially entangled objects, there's a little bit of connection at the junction between the two. They're not totally unentangled, but they're basically the state of a trivial object can be viewed as just a direct product of the state of the left part and the right part, with a little bit of entanglement at the junction where they're joined together. But basically, a measurement over here will not really affect anything that happens over here. Well, on the other hand, if I take the topologically non-trivial system, which actually has to have some kind of edge around it, which is different. If I try to cut the regular system in half, I can basically pull it apart and separate it into these two different quantum systems, which are just direct products of each other with each other. If I try to do that for the topological system, it'll initially resist me trying to pull apart, because essentially there's a long-range kind of entanglement between the left and the right side, which is responsible for terminate these edge states. The edge states are there because they have to terminate some kind of strings of entanglement through the system. So eventually, if I manage to cut it in half, the entanglement will be gone, but it'll be replaced by the edge that I created will now be protected by the termination of the cut lines of entanglement between the two systems. And there'll be an edge state that goes all the way around. So it's a bit like a bar magnet, where you can't chop a bar magnet and just get a south pole and a north pole separate. That's actually not topological, that's long range order, but the topological states have some kind of property like that, where I can't avoid the edge state. So in principle, topologically trivial states of matter can be assembled by just bringing the atoms together and putting them next door to each other, with all the electrons still remaining bound to the atoms during the process. So when you study simple quantum mechanics of periodic solids, you find that there's a band description, but there's also something called a 1A orbital description, where you can sort of basically trace it back to just the separated atomic description. Well, topologically non-trivial states of matter, they cannot be adiabatically or continuously connected to the isolated atom state. At some point, when the atoms are brought together to form the solid, bound electrons have to get liberated from their atomic orbitals and rebound in a new state, which it has entanglement, non-trivial entanglement across the system. And one of the striking characteristic properties of band insulators, which are topological, is their edge states. And this took a long time to see as a general principle, but in fact, you can see it back in old work, going back even as far as Shockley in 1939, who managed to do a toy model calculation of a one-dimensional line of Theris atoms in one dimension, little quantum wells. And it was amazing. You could do this kind of calculation before electronic computers were around. I think these calculations were done in a room full of an integrated circuit full of humans, typically female at that time, who would each have a kind of add machine and do some calculation on this mechanical adding machine or whatever, and then hand the answer to the person at the next desk or something, and they do a integrated circuit type calculation to do these kind of things. But what you actually see in this very old calculation is, as I bring the toy model together, if the atoms are widely separated, so there's really very little tunneling between the quantum states in the bottom center of each of the little wells, you just get the widely separated atoms. As I bring them together, you can see that at some point suddenly something happens, right? Essentially, the bands overlap, or there's an inversion of the bands at the Brillouin zone edge, the pi point in the band structure, and the bands touch, they cross, and after that you're left with two states, and the two states are localized at the two ends of the chain. So if I take this system here, and these are the edge states, of course, and if I put if I fill all the levels up to this below this point, so there's one electron less in the solid than when it was isolated atoms. There's one electron missing, but there'll be half an electron at one end missing and half an electron at the other end missing. So you start to get all these kind of strange things you see in topological materials, like fractionalization of charge. So there's half an electron at one end and half an electron at the other end, and or half a hole rather. Half a hole, there's one electron missing here. If I put the chemical potential above the two levels, then there's one extra electron, there's half electron at both ends as well. So so you see this feature, and of course I can never make a half electron sit locally by itself in empty space. So you start to get weird things like fractionalization of charge occurring in topologically interesting materials. And there it is, there's the picture, right? So we have this fractionalization. So in fact, the fractionalization principle occurs in interacting systems too. We can have we only had fractionalization at the edges of the chain, but here if you have some structure like a density wave or something, in a crystal, which comes about through electrons repelling each other. The lowest energy state of the system is to put one electron in every second site in this toy model. And if I remove one electron, so I have 3 empty sites next together, energetically they can split by one particle moving along, and you can see that one electron was removed, so there was a charge 1 deficit at that point, but it can split up into half an electron. So you can get this type of unexpected fractionalization occurring in these topological states. So in atoms, in a magnetic thing, in heavier atoms, the electrons in a group of atomic orbitals, they get locked together and they're always parallel. And this is what gives rise to one kind of magnetism, not a metallic magnetism, but magnetism of an insulating magnet, ferromagnet. So the total spin, the spins of electrons come in these, is conventionally quantized to be spin 1/2. And so the total spin of a complete group of these things is locked together with an integer or half integer number of value of spin, which is either an even or an odd number of electrons. So conventional magnetic ground states have long-range order. The one you can pick your paper, the ferromagnet, which is basically the magnet that can pick up a paper clip, has all the spins direction arbitrarily selected, but pointing in the same direction. They can point in different directions, and that gives you an interesting domain structure in the magnet. But the simple case, if the magnet's shape tends to select the direction, so pointing up or down along the bar, along a bar magnet, are the 2 natural positions. So in antiferromagnet, it can't pick up a paper clip, but it's still a similar thing where the spins on neighboring atoms are opposite direction to each other. So there's still a fundamental direction where the A site type of sites are all pointing one way and the B sites are pointing the opposite way. And they had to make a choice about which direction to point in. So this won't pick up a paper clip, but it's also a magnetic state. And around about 1981, I looked at this problem, which people had sort of decided they knew how everything went. One dimension was a little special because of quantum fluctuations of the direction. But the previous expected states were basically, everyone in magnetism had been working with states which didn't have entanglement. Basically, they worried about the directions of the spins being special, having chosen a direction to point in, but no basic entanglement between the two. So if I take the standard picture of the magnet and just chop it in half, I can just pull the two antiferromagnets aside, and I'll get there's nothing special happening when I chop them in half. But on the other hand, the state I discovered turned out to have a very simple representation in this picture, and little toy model pictures play a tremendously important role in all this new topological physics. They allow you to think very concretely about things. So this state here, the spins, it's a spin 1, so there's actually 2 spin halves. They it sort of factorizes or fractionalizes into 2 spin halves, and they join hands to form something like a chemical bond with the spin, half the spin on the next site, and you get this entanglement bond, this bond of singlet pairs across the system, which is now entanglement, so I can't cut it in half without doing something. And because you join things in half and there's 1 spin left over at either end of the thing, we get this typical edge state thing. These were built out of spin 1 atomic spins, but there's a spin half, a local spin half somehow got created at either end of the chain. Well, anyway, this state, because no one had really thought about this stuff, it really shocked the magnetism community, and it provoked a lot of controversy. And I guess the fact it was controversial, I couldn't understand why it was so controversial, but people had dug their heels in about the old way of looking at things. So after this thing was denounced by kind of top people in the field for a while, the experiments eventually came along and showed this was not in fact what happened. And this actually shows you one of the important things, the link between theorists and experimentalists, and especially material scientists, because all these recent developments in topological materials, they've really been brought to fruition by the amazing advances in material science that made allows people now to design materials to fit with a theorist toy model, rather than theorists having to try to twiddle their toy model to fit the pre-existing material. And the designer material that was used for this was an organic chain which had spin 1 nickel atoms in it. Anyway, the controversy in this thing was actually very good, because it actually led to, experimentalists on the controversy between theorists makes experimentalists very happy, because, well, experimentalists, the best thing for an experimentalist is, of course, to prove a theorist wrong, right? But I guess the second best thing is to prove a theorist right when there's a controversy. And it's a powerful motivation. And in fact, even theoretically, a lot of the fact there was a lot of controversy about this led a whole lot of new techniques like the like matrix product states and density matrix renormalization group methods, which have become really key tools these days, were actually created to try and address this controversy. So the struggle between ideas is an incredibly good thing for innovation in science, because people come up with ways to give their how they can give some input to the problem. So anyway, the meme, this thing is an entangled line of people holding hands. Now you'd say that without any kind of, no one's been disfigured or something, that hands always come in pairs, usually. And how could you get an isolated hand? Well, you've got this thing where the people all joined hands, so the only free hands were at the end of the chain, so they came in singles rather than doubles. Okay. So anyway, so this was kind of, the chain ended up on my Nobel Prize certificate, even though the actual toy model that was used to represent it, it wasn't the one that I used initially. Okay, so soon after this discovery in magnetism, Michael Berry, who's in Bristol, he discovered the importance of what's now called the Berry phase in adiabatic quantum mechanics. Basically, thinking about if I slowly rotate a spin, the direction of a spin around the closed path, and I get back to where I started from, the quantum state is apparently the same as the original state, but actually quantum states are ambiguous up to a complex number of phase, which I can't measure. I can only measure the difference of phases between two quantum states by an interference measurement. So what Berry found was that if I rotate the spin through a little angle, through a closed path on the surface, so the point on the surface of a sphere is a closed path, the phase change is related to the solid angle subtended by the path. Actually, it's S, the spin, times the solid angle. And solid angles are defined modulo 4 pi, because the surface area of the sphere is 4 pi r squared. Now, on a sphere, you can't say which part of the surface of the sphere is inside and which is outside the contour. So if I say the phase change is S times the solid angle enclosed by the path, you say, is the region enclosed by the path this region, or is it the other region, right? And one is 4 pi minus the other one. So this thing is fundamentally ambiguous modulo 4 pi, but that's fine, because 4 pi times spin is 2 pi, and phases are only ambiguous modulo 2 pi anyway. So actually, this is another way to prove that spins have to be quantized, so 2s is an integer, rather than the algebraic way that you usually learn with the raising and lowering operators in a quantum mechanics class. Anyway, Berry's phase has really been a seminal development in understanding of modern understanding of quantum mechanics. So quantum Hall fluids are perhaps the clearest example of the topological states. And again, Klaus von Klitzing discovered that this measurement of this is actually the inverse of the conductance, the resistance, but the whole conductance of a bar of material, the voltage, I dub a current through it, and I measure the voltage difference between the sides, and relate that. The voltage to current relationship gives me the current to voltage relationship give me the whole conductance. And he discovered the whole conductance was a whole number, an integer, times fundamental constants E squared over h. And if I know E squared over h, and I know the permittivity of the vacuum, which is 577 ohms or something, the ratio of this number, which is inverse of 25,310 ohms to that gives me the fine structure constant. So he was amazed that you could measure the fine structure constant to 6 or 7 figure accuracy in a little piece of rather dirty looking semiconductor in a high magnetic field. And this discovery that this is now went to even much larger precision, and now this has been combined with the Josephson effect, the AC Josephson effect to actually replace the kilogram, so which was kept in a safe in Paris. That basically Napoleon had made France the imperialistic ruler of the world as far as weights and measures were concerned, because they had the kilogram. Now anyone can build the kilogram using the quantum Hall effect and the Josephson effect, and it's liberated our system of units from lumps of platinum in a safe somewhere. So anyway, the topological aspects of the fractional of the quantum Hall effect took some time to appreciate. People mainly thought about how come this stuff is robust against dirt, but you can actually see when you look more closely at it. For example, Bert Halperin pointed out that at the edge of such a system, inside the material, the electrons in a magnetic field, they're tied to the plane, this two-dimensional plane, but inside the plane with the magnetic field going perpendicular to it, they go around in little circles. But if the circle is close to the edge, it ends up hitting the edge and bouncing around. And it goes around the edge. Something goes around the edge in the opposite sense to the circles here, the skipping orbit. And actually, in a toy model version of this thing, the quantization of periodic motion gives rise to a gap in the middle, which gives you stability. But the edge gives you a thing that it pins the Fermi level. So the magnet, so long as as I change the magnetic field, states flow up and down like through a pipe from above to below, and they fill as they pass through the chemical potential. So as I fix electron density, the system will always stay in this system where everything in the lower orbital is filled and empty in the second one. And it's not you don't need to fine tune the magnetic field, and it has the edge states give this whole thing a stability, which was totally unexpected. So it's a topological issue with one-way transport going around the edges. Well, my co-laureate David Thaulis with some postdocs, Komoto, Nightingale, and Marcel Denys, he proposed that they work on instead of working on a problem with a random dirtiness inside the material, which is incredibly difficult to work with mathematically, he made the thing a solvable toy model by saying, what happens if the dirt in the middle of the material is just replaced by a periodic potential, right? And so we actually know how to deal with periodic potentials by Bloch's theorem. Now they're slightly different when they have a magnetic field on it. You have to have it finely tuned that the magnetic flux through one unit cell is a rational number, etc. But anyway, they worked with the toy model where you could actually do calculations on, which is a really important thing about toy models, that you can take a calculation from beginning to end. And they discovered a strange formula which they recognized had to be an integer. And in fact, with a mathematical physicist at Princeton, Barry Simon, who heard about both discoveries. He'd heard about the Berry curvature developments that Michael Berry had found, and then he heard about the formula that someone else told him that that Thaulis and co had discovered a strange formula that gave you an integer out of it, and he recognized and made a connection to the Gauss-Bonnet Chern formula, and pointed out that the two things were basically related in this way. And so this is how donuts actually come to play some role in quantum mechanics. So in retrospect, all this stuff was done in high magnetic fields, and the Thaulis result was actually, it took a long time to realize it wasn't specially restricted to the particular case of the specific features of high magnetic field band structures that he looked at, but it also applied to a model with no magnetic field at all, which I stumbled across in 1988, basically I was trying to argue that the key thing for the quantum Hall effect was not the magnetic field, but broken time reversal symmetry. if you have edge states that go one way around the system, then around the edge of a system, that if you take a movie of it, you'll see it looks different from if I show the movie backwards. So one-way motion is clearly breaking time reversal invariance, but one way to get it is have a magnetic field and cause the particles to go around in these little circular orbits. But without a magnetic field, they don't go around in circular orbits. But anyway, it turns out band structure effects using the Berry curvature can actually give rise to something similar. And this is actually what gave rise eventually to this current topological insulator idea. It's a very simple toy model, which actually is the same model, a related model to what's used to measure graphene these days. In fact, in my paper in 1988, I gave this toy model and said this is like a single layer of graphite. But of course, no one would ever be able to make a single layer of graphite. Well, it just took a bit of Scotch tape and there was another Nobel Prize floating around for graphene. So if I look at the graphene problem, we kind of see some of the issues. That the graphene actually, when you look carefully at it, in particular, there's one edge of it like a honeycomb, but if it's got an edge which is called the zigzag edge, the symmetries of the graphene toy model for graphene show that there's actually a bound state at the edge which connects these two things which are called Dirac points, which touch in graphene. Graphene's properties are due to the fact that it behaves like a Dirac equation near the Fermi energy, and they have these Dirac points which touch. So graphene is a semi-metal with bands that touch, and at the edge of the system, there's actually, if I project the band structure onto the edge, there's an edge state which connects these 2 points and is connected to them. Now the touching of the graphene bands is due to 2 symmetries, time reversal symmetry and spatial inversion symmetry. And if I break any one of those 2 symmetries, I must open up a gap in the system and break the Dirac points apart. If I do it in a boring way with broken inversion symmetry, then you either find the 2 edges, the edge states remain attached to the 2 bottoms of the conduction band or the 2 tops of the valence band. But if I do it in the time reversal breaking way, then the other thing happens, and one edge state is attached to the lower Dirac, the lower point of a split Dirac point here, and the other one to the upper. And that gives you a continuous connection where states, as I change the magnetic field through the interior of the sample, I can pump states along this. It's like a plumbing connection that connects the conduction and valence band continuously. And quantum states, which can be occupied by electrons, can move up or down this little pipe. And that way you get actually a quantum Hall effect, which you can say that if the system is in an energy level is in the gap, then the number of electrons in the lower band changes with magnetic field, which is exactly what happens in Landau levels in the high magnetic field case. So actually, this was predicted in 1998, and it's got this really neat stuff with one-way transport. But it took until 2013 for experiments to confirm this this so-called magnetic topological insulator. It's actually showing how Chinese science has advanced tremendously, because some of these developments actually now occurring in China. But anyway, so the edge states are very interesting because without these, without the huge magnetic fields, we still have a system with one-way transport along the edge. It's kind of like, if we didn't have a rule of the road where you drove on the left or the right, depending on whether you're in Britain or the United States, the traffic would be a total mess. But by separating the traffic moving one way from the traffic moving the other way, everything moves more smoothly. And there's actually a lot of possible technological interests in one-way transport systems. And in fact, you can do it in light, which I will have to skip. But the same kind of principle, it's a topological principle of one-way transport. Once you find it in one place, you can find it in other places too. The topological insulators was a copy to, in fact, to get rid of the time reversal breaking, you just take 2 copies for spin up and spin down of the original model, and you can find systems where up spins move one way along the edge and down spins move the other way. And that time reversal invariant thing was the key to finding that you could actually obtain these topological materials, not just in a 2-dimensional system, but in a 3-dimensional system like real crystals. And this has given rise to a huge kind of developments is really the fact that these occur in three-dimensional crystals, and that people found there was topological materials sitting on their laboratory shelves, which they hadn't known were topological. It turns out the only way to see they're topological is to look carefully at the edges, and you see these unusual edge states. And no one had thought there was anything like topological insulators. So even they'd been doing lots of ab initio, huge calculations of properties of materials, no one had really thought to think closely about the edge of the material where all the interesting stuff was happening, at least in these so-called band topological insulators. And now there's all kinds of other things like wire points, and it's led to a whole new reassessment of the theory of electron bands to realize there was a topological aspect there which had really been missed. Okay, so let me move on. So the integer quantum Hall effect was soon followed by a much bigger puzzle, which is called the fractional quantum Hall effect. And this thing was a much richer topology, it turns out, than these kind of free electron type of systems we discussed now. And again, another Nobel Prize came out of this thing, right? So there was, I guess, only 3 people can get a Nobel Prize. So the guy who made the device didn't get it. But these guys measured it, and this guy came up with the beautiful, unexpected theoretical explanation out of the blue for it. So this actually is the device in which the fractional quantum Hall effect was seen. And you can see the forgiving nature of the topological states, right? I mean, you wouldn't get a job at Intel for your soldering abilities if you showed this as an example, of your work, right? But nevertheless, this messy-looking piece of junk actually showed this amazing effect. So in the fractional quantum Hall effect, you start to get the fractionalization in the interior, right? You find you have this amazing wave function, which Laughlin kind of found by accident again. He did a 3-body calculate. This was unexpected from the viewpoint of how people viewed many-body wave functions at the time. Most theorists at the time of the fractional quantum Hall effect thought that Feynman diagrams was the way to go, because they'd been so successful in theories of superconductivity and the like. And again, there was no one had even dreamt of wave functions that looked like this before. And Laughlin just discovered it because he did a 3-particle numerical calculation on a computer, and the system was simple enough and he found that a low energy state in the system, and the system was small enough that he could actually transcribe the results from the computer into equations on a piece of paper, and voila, there it was. But in this system here, we have again, we have the features of things going around one way at the edge, but now it has objects inside the system are different from objects outside. Outside the system, you just have regular electrons with charge E floating around in empty space. Inside, an electron divides up, at this case 1/3, filling into 3 1/3 charge objects. Okay, and furthermore, these 1/3 charge objects are not fermions or bosons, which in this case, if I exchange a pair, do I get a plus sign or a minus sign? No, I get a complex phase when I interchange them, and I have to interchange them 3 times in a handed way in order to get back to where I started from. So you get this nice picture of braiding, the history of moving these things around inside the system. And as they move around and you keep them far away from each other, you end up their paths you can get back to the same state 2 different ways. You can braid them one way or the other way, or twice, and you get instead of getting a plus or minus 1 phase, you get a phase which is a multiple of 2 pi over 3. So in these kind of systems, when you actually look at them numerically, you can it's a very simple Hamiltonian you can look at. You project into a given so-called Landau level, but basically these systems have an energy gap between if I do it with periodic boundary conditions, I get a topologically degenerate ground state, which has inversion symmetry, separated by a gap from any excited states. And in fact, from these numerical calculations, we can see the excitation energy and what the excitations are. And because there's an energy gap between isolated quantum state, even though this is like a liquid type state, there's no kind of sound waves in it. So this state is incompressible. It doesn't transmit sound waves. So quantum incompressibility is actually extremely different from the notion of a classical incompressible fluid, which is just a fluid like water is almost incompressible, right? But the oil inside the lift that the car mechanic uses to lift your car up, that's the hydraulic lift, is using the essential incompressibility of oil to push your car up. But in a classical incompressible fluid, the speed of sound actually becomes formally infinite as you go to fully incompressible. That's why a completely incompressible classical fluid violates relativity, because the speed of sound in it would become larger than 3 times 10 to the minus 10 meters per second, right? But quantum incompressible system is rather different. It doesn't transmit force at all, because there are actually no low energy excitations that can carry sound or transmit pressure. So anyway, the Laughlin state and these other early fractional quantum Hall states are what we call abelian states, and the more remarkable ones, which we hope to use for quantum computing, are so-called non-abelian states, which are pioneered by Moore and Reed, and they can hide quantum information in their entanglement structure. And so in this case, we have the non-abelian states. As I move one of these defects around each other, I don't just get a phase. I actually change between there's a hidden manifold of low energy states, and I go between them by manipulating the things, and I can store information in the hidden states. And this was first pointed out by Moore and Reed but the whole subject took off again, because around the late 1990s, Alexei Kitaev pointed out that this was actually seemed to be a natural platform in which you could implement quantum computing in a topologically protected way that protected it from the environmental processes that could degrade it. And the information processing notionally in this scheme is done by braiding the objects around each other and changing the internal state of the system. So actually, this has remained a very theoretical thing. There's been a big effort to look for topological braiding and things, and Microsoft in particular funded a group which has been trying to do it, not initially in the quantum Hall effect, but now in some other semiconductor system. And but only just this year, finally, there's been semi-convincing kind of experimental demonstration of so-called anion braiding of the abelian variety, the Laughlin state variety. Here you have a system where you have some kind of trap in a semiconductor, a little kind of quantum dot, and depending on how many, if an electron moves around here, or if charge tunnels across the boundaries between these two things, it actually has to be a flow of these quantum fractional excitations have to move, and the phase they pick up depends on whether there's one inside the thing or not. If I put an extra fermion inside this loop, it's not going to change the phase of exchanging these other two particles around it, or moving a particle around it, because it's not an exchange, it's going around, it's a double exchange, really. If I move around here and there's a fermi in the middle, that's not going to affect anything. But if there's an anion in the middle, it'll pick up a phase change. And in this 1/3 state, you pick up phase change modulo 2 pi over 3. So you can count, the phase counts the number of anions sitting inside the trap by modulo 3. And as I change the magnetic field, the number of anions will jump. There'll be the lowest energy state of the system will jump from 3 to 2 to 1, whatever. And what you actually see as I change the magnetic field, these interference patterns, which tell you what phase I get for going around the thing, have like a slip. It's like an earthquake or something that happens when the anion content of this thing in the middle changes. And that's what these glitches in this pattern of interference fringes claim to be seen. So this is actually remarkable. We finally, only this year, been able to actually see some honest looking experiment more evidence for anyons. It's just like it took so long for my original magnetic topological insulator to come to fruition from 1988 to 2012. Here, these original anyons goes back to about 1990, and now it's taken till 2020 to actually turn the theory into something real. So anyway, in this picture, where's how you do the quantum computation? You can think of this system as a little vortex. You think of these excitations as vortices in a quantum fluid. And it's got this fluid in a two-dimensional puddle, and it's got these kind of one-way edge states going around it. And the vortex has a little opposite direction edge state bounding it. So there's a kind of little thing, and in this case, it turns out you can these kind of vortices in the Mouride or non-abelian case, you actually can't create these vortices individually. You can only create a pair of vortices. So I can create, by removing some electrons, I can removing one electron. These actually vortices carry a quarter of an electron charge, or minus a quarter of a whole. So if I remove one electron from the system, I actually create 4 vortices. And if I move one around the other, that's the braiding, and the information storage happens. And how does that happen? Well, first of all, let's have a look. There's a hidden pattern in this thing, and let's have a look. So essentially, the history of how these vortices were created leads to a hidden entanglement pattern in the system. So this, if I created, if these two vortices were joined together before and I pull them apart, they leave a kind of entanglement trail connecting those two, and the other two had to be connected by their own entanglement trail. But if I move this one around the closed path around here, it kind of passes through this thing and grabs some of this entanglement tail, and I'll end up with this pattern. And if I look at it, all I see is 4 vortices. I can't see the entanglement patterns directly, so I can't tell that these two things are 2 different quantum states. But this is enough to give you a single qubit, and it turns out the simple braiding operation in this Mouride state corresponds to rotating the block vector, or the block vector in the block space on the block sphere of the qubit, from pointing towards the North Pole to, say, pointing along the equator somewhere. So I can move. I'm processing the quantum state by braiding these things around. I have to keep them far apart. And that way the information is spread out and can't be affected by coupling to the local environment. I could take a gun and I could shoot a hole through this system. This is the US, of course, so I think of a gun analogy. So I shoot a hole through the system and it blasts away stuff here. But provided that entanglement information didn't happen to be exactly at the site of the bullet, which is proportional to the size of the hole compared to the size of the system, it won't be affected, right? So I have this non-local storage of information that protects it against violent local events. And in fact, if I do an actual calculation of these things, you can actually see this is the same toy model system. It's put on a sphere for whatever technical reasons. But actually, the 2 possible states of the qubit with these 4 charge minus a quarter objects well separated. If you look very closely on a finite size system, you see little kind of interference pattern between the two, which you can in fact distinguish. I can look at the interference pattern and say this is the up state and that's the down state of the qubit, and I could look at the interference pattern and actually see it, but it's actually spread out through the system. And as I make the system bigger and bigger, these interference fringes become exponentially small, so they're really unmeasurable by any local measurement. And so you can see the information is contained there, but it's been spread out over the whole system. Right? So anyway, the quantum physicists have this beautiful dream of a topologically protected qubit. As I say, it's taken its time. We don't actually we have working qubits for so-called NISQ or noisy intermediate scale quantum computers. Now Google and places and IBM have all these things, and they're claiming quantum supremacy at 50 qubits. But these are all unprotected qubits. In that kind of quantum computation, it's really a question of carrying out the same computation many times, and hoping nothing goes, hoping you manage to get through from beginning to end without a decoherence event. And I guess if you get the same, if it's a complicated, if there are a lot of possible answers and you get the same answer twice or three times, I guess you could identify that as a case of the calculation where you actually did manage to go through to the end without encountering an error. But basically, if the calculation is more and more complicated, there's no way you'll get the same answer twice, and there's no way to know whether or not you got the right one, and most likely you didn't, because almost always some decoherence event will have occurred. So the qubits here are not advanced at all. People were dreaming that they would, in 2017, it was predicted to be the year of braiding by some of the people in the Microsoft group, but 2017 came and went, and there's still been technical complications. So it's nice that at least something has finally emerged this year. So whether we're going to get quantum computing computers or topological quantum computers, I think it's a more realistic dream. I mean, the dream of fusion power has been around the corner for many years. Quantum computing has been around the corner at least for a while, but we'll find out. It seems that the possibilities of going around are rapidly advancing. So I think it's a reasonably realistic dream that we will see some interesting new quantum information technologies. Okay. So what's the Microsoft group working on now? They actually have a superconducting wire, so-called Kitaev model. Again, it's a one-dimensional chain. And the crucial thing is that let's see if I got that. Let's see if I got it here. That in this system, a single electron orbital, which can accommodate one electron, formally, at least mathematically, can be split into two halves called Majorana modes. So a regular electron orbital is two Majorana modes at the same place, and the formal description of the system is either as electrons or as Majoranas. But there's nothing, the Majoranas are purely a mathematical device because they're both sitting on the same site here. The amazing thing in the conducting wire chain is that the coupling, when you couple this thing to a superconductor, it actually allows it splits each electron state into two mutual Majoranas, but I can then have a rearrangement transition where instead of the two Majoranas being on the same atomic site, the pair forms with the neighboring sites, one to the left and one to the right. And if that happens, you actually get one of the green Majoranas on one site and one of the red Majoranas at the other end of the chain. And this is actually sort of the same meme as the original spin chain model I discussed, where you ended up splitting a spin one into an atomic spin one into two microscopic spin half objects, one isolated in each end of the chain. You wouldn't have initially thought you could split a spin one into two spin halves, but here you wouldn't have initially thought you can split an electron orbital into two half orbitals, which are now called Majorana zero modes. But again, the crucial thing was that it now becomes not just a formal device, but a real device, because the two Majoranas are now physically separated, spatially separated at either end of the chain. And in the Mouride case, the vortices each carry one of these Majorana modes. So in the 1D system, there's kind of toy train-like devices for how do you interchange them and do the braiding, and probably we won't see. But anyway, this is the similarity in all the things. So in fact, these topological principles all become reasonably similar and simple when you look at them in the right way. So this is all just one of the current approaches looking for quantum computing. Like I say, the other unprotected things, transmons at IBM, ion trap bits at Michigan, NV centers in diamonds, etc. These are all kind of making lots of progress. I don't know what we're going to come out of all this thing, but I'm sure we're going to learn a lot of new things about quantum mechanics in this second quantum revolution. So one of the morals of all this story is that there are a lot of pieces to tie together here, right? My viewpoint has been the toy model builders working with simplified models where all the unnecessary details have been thrown away so that you can actually do a calculation and see something amazing happening. Of course, you do need some deep mathematical principles like the Gauss-Bonnet-Chern theorem, etc., to actually understand the strange things you might have discovered in the toy model. And you actually, of course, need to make all this thing real and not just theorists kind of playing games with each other, is to actually have the material science to actually turn the toy models into reality and then confront us with systems that actually behave, right? So now I have a kind of, so finally, my contribution, I listed two things here. Both of them really came about through I wasn't looking for anything when I wasn't looking for those things. I found them sort of by accident. I was looking for something else and found something unusual. So my message to all the people, anyone who goes into science, I think you don't actually need to be a special genius. Einstein is special. He did his thought experiment about what things would look like if you traveled at the speed of light and things with a light wave. But in some sense, also he lucked out because he had to even be interested in this problem. Like something had to draw his attention to think about what was the contradictions between Maxwell and Newton, right? Well, here you just need luck, basically. You can be very brilliant and you can do fantastic work, but to actually, these new things are unexpected. So actually you need luck to stumble across something truly unexpected. And those things are only out there because no one expected them, because if anyone had any idea there was something out there, so many talented and brilliant people would have been out there searching for it and would have found them already. So you need to have luck to be walking along a path that takes you next to something unexpected. You actually do need to have the preparation from your previous training to actually recognize that something you found was unusual or remarkable. You can be walking down a path, kicking rocks, and if you're not looking at what your feet pull up, you could kick up a giant diamond, could be unearthed by you and kicked. You can kick it around, but if you didn't look, you just walk on by and leave it behind. Maybe then someone else will probably come later, hopefully, and find the diamond. But you basically need the preparation to recognize what you found. And in fact, if what you find is something that contradicts the current way of thinking, and unexpected things are most likely to contradict the current way of thinking, you'll probably meet a lot of opposition to it. You really have to fight for it and have commitment to follow it through and fight for it. So because these are the same things, luck and commitment and preparation, as what anyone, I guess, giving a motivational talk at a business school graduation would say, right? But it's probably true. You need this in all walks of life, and luck is one of the most important features for at least to end up in something like a Nobel Prize, right? You, of course, don't need luck to be, you can be brilliant and do great work, right? But you'll always be kind of explaining something that someone else found. Okay, and I think that's the end of the talk.
All right, Professor Haden, huge thanks for a wonderful and inspiring talk. It was an enormous pleasure to have
you, if you're lucky enough, whatever you're doing, I think you have some chance. It may be a very small chance, but because luck is around there, if you keep your eyes open and whatever you're doing, if you take the time to study some kind of anything unusual that occurs in your research, if you're too motivated by going along a straight path and don't have the time to look at unusual things along the side, you'll miss things. But if you take a little bit of time, when you find something unusual, most of the time it will just be something unusual, but occasionally it be something tremendous. Okay.
Thank you so much for such a for such a great message, and it was, of course, an enormous pleasure to have you speak at our society. Maybe actually move to the Q&A session right
Sure.
now. There are many questions from the audience, so perhaps let's start. So the first question. Right, what's your view on the recent developed non-Hermitian topological matters?
Oh, it's very interesting. I mean, it's certainly in photonics, right? I mean, I've worked on topological photonics, and there you don't have charge. the photon is not a conserved object, like doesn't carry a conserved charge like an electron. So of course it's a natural thing to have loss and gain, and you know, a lot of interesting things. There was recent work showed you can get I guess when you have non-Hermitian matrices, for example, you have these exceptional points where because the eigenvectors don't have to be orthogonal, you can end up special points called exceptional points where eigenvectors become parallel and the basis becomes rank deficient, right? So now people found that you can have a 3D non-Hermitian crystal and have exceptional point edges or something that can't be got rid of, right? So it's actually a very interesting field that's subfield, and especially, I guess, once you remove the conservation aspect of things that you have for electrons. And so the original topological photonics, I briefly touched on it somewhere back here, actually. There was there's topological photonics. You can get Chern number edges. Right, so this case, there's energy, the photon, the only thing the photon carries is like energy. But if the system is harmonic or Hermitian, then the photon carries a conserved amount of action and it travels as an entity, of course, but there's nothing, because it's not carrying a conserved charge, it can decay and it can be pumped. And so a lot of things change when you go to non-Hermitian, but it's an extremely interesting subfield, yeah, non-Hermitian. And there's a lot of interesting aspects in lasers. You can get interesting kind of edge modes, and the way they get pumped is different.
All right, thank you for your answer. Now there's a question actually about the motivational aspects, and actually coming back to your final message and the material flag and commitment and motivation. Right. So, what motivated you to study graphene when exploring the zero magnetic field quantum Hall effect? That's another question from the audience.
Okay, 1 second. Okay, no, actually, what happened? I mean, there was a paper, I guess, by Eduardo Fradkin and collaborators, which sort of claimed to get a quantum Hall effect without through spin orbit coupling he called it in essentially what we'd now call a spin orbit coupled non-magnetic topological insulator. So I felt so I started off writing a comment on this thing in Physical Review Letters. Right? It seemed to me it had to be wrong, because you needed time reversal to get the quantum Hall effect. To get the one-way aspect of things had to break. You had to break time reversal, and they were asserting you didn't have to break time reversal. You could get everything out of spin orbit coupling. So when you put spin orbit coupling, got the Pauli matrices in there, and sigma 2 is imaginary. So you get imaginary numbers floating around in the Hamiltonian, right? So it seemed to me they had to have made a technical mistake somewhere in the thing, and because the claim was that the input model didn't break time reversal invariance, and the output seemed to show some kind of quantum Hall state. So somewhere there was a non sequitur going from beginning to end, and this started off as part of this ridiculous kind of comment. You have a comment and response cycle in Physical Review Letters. Basically, the commenter says something, the authors don't understand what he's talking about, and two people are talking at cross purposes, right? So this actually, I just came up with, let me design the simplest possible toy model to illustrate the point that you need broken time reversal invariance to get quantum Hall effect. So I came up with this toy model of graphene as a simple model you could do a calculation on, and then I realized, wait a minute, I mean, this is very interesting in its own right, not just as some kind of point in view of some kind of argument about whether some other paper was right or wrong. And I hadn't anticipated that. I hadn't realized that you could get a quantum Hall effect without a magnetic field just from these Chern things. Okay, in principle, one should have realized that from Fowles and Co.'s work, but Fowles and Co.'s TKN work focused on the very special kind of band structure you've got by combining periodic potentials with magnetic fields, and those require very fine tuning between the magnetic field and the size of the unit cell, right? So those were a very delicate kind of formal thing. While in retrospect, it became obvious that you didn't need to have the magnetic field. In fact, once one saw one didn't need the magnetic field for electrons, eventually you could see that you didn't need to have fermions or charge conservation to get some analogous effect with photons, right? So it's really, you're limited by the way you think about things limit them, right? You need something to step around and get a broader view of it. And this was an accidental feature, and I just knew about the graphene band structure as a very simple toy model to play with, and suddenly there it was.
All right, thank you so much. We have another question, about the use of topologically protected states for quantum computing. And the question is, while this may bring about well-protected qubits, and is the technology scalable to the level where qubits could be produced in the millions required for a practical quantum computing?
Okay, well, the basic problem here is we don't have the technology yet. I mean, it's still a theorist's dream. Some people might say it's a theorist's pipe dream, right? But in principle, the fact that the quantum information is hidden non-locally in these internal topological manifold of states of the system that you can manipulate by braiding the non-abelian anyons around. That protects it. Now, the information is you still, to actually access the information, you have to bring some of these things close. You have to bring a pair of these anyons together, and then you can then as I try to show in this picture here, there's the information is actually stored in these interference fringes well away from the yellow dots, which are the local defects. When you bring it together, as you make them far apart from each other, these are exponentially, the wiggles become exponentially tiny, and so they're not affected by a local measurement. As you bring them together, you eventually can have a noticeable difference between the different states of the system. So, of course, to actually input and out, read in and read out stages of the thing will still be dangerous, right? But the danger of losing the information will only be in the read in and the read out state. Once you put the information there and spread it out non-locally, you can carry out many braidings, a large number of computational steps without endangering the information. Okay, at least in principle, theoretically, right? So that's why people believe it's a scalable thing, because the length of it would not be affected by the length of the program, right? The read in and read out are just initial and final events. The unprotected thing, the longer the program runs, eventually there's an exponential fall off in success probability, right? The chance of having a decoherence event just increases linearly with time in an unprotected case. And so a long sequence of quantum computation, the longer it is, the more chance the chance of it failing is bigger and bigger. It's exponential, right? So this is protected. Now, there's all kinds of other issues about, kind of another any from outside the system drift in and ruin things. And we actually don't really know what quality we get these things, because we actually haven't managed to build such a qubit yet. So, I mean, I don't know how much longer, Microsoft will be putting money into their semiconducting, superconducting wire qubit braiding experiments, but because nothing has come out yet, but so we're well behind in the practical thing of actually even having a working qubit. While ion traps and ions on chips and transmons and all these things are and all these things, the other qubits, the non-protected ones, are racing ahead, right? So to actually understand the full scalability of it, as opposed to the theoretical scalability, will require one to actually be able to understand a real device and see what maybe there's other unexpected limitations that the theorists haven't thought up, right? So, I mean, I can't advise people to go out and put their pension money into a startup doing topological quantum computation at this end, but I do think it's a very interesting, it's intellectually a solution to the problem. Whether it practically is, I don't know.
Okay, thank you. We have a few more physics questions. So there is one on antiferromagnets and entanglement. So reformulating this, you mentioned that antiferromagnets don't generally entangle much, but I was under the impression that frustrated antiferromagnets show a very high degree of entanglement, and this is the part of the reason why they are the subject of much current research. Could you comment on this?
The frustration isn't really. Let's see if I can find the right. The frustrated magnet picture is just that they're not in a regular array. They're in a random array, or they have a preferred random state. So this is an ordered magnetic state, up, down, up, down, up, down. Because the exchange between these two is negative, but if I have frustrated where I have negative exchanges between all of these things, then the decision about which neighbor to be anti-parallel to is difficult, and that's where frustration comes in. So the frustrated system has a large number of possible states, rather than just two possible states or something. Not quite that, but something like two possible states I've drawn here. The frustrated one, but it's not entangled, right? So the models for frustrated quantum magnets in general are classical. So you might hear that one of the proposed uses for quantum computers, which strikes me as a bit crazy, but apparently is that you can use it to you could in principle use it to discover the ground state of a classical frustrated magnet. Of course, you can translate that problem of search, which classically would require you just to search through all the possible states of the system to find the one which has the lowest energy. The basic philosophy of quantum computing is essentially just like quantum mechanics says that if there are two doors to a room and you're in a coherent state and you leave the room and no one sees you leaving, you could have some interference between going out through one door and going out through the other door. So the quantum mechanic, the kind of meme for quantum computing is you're basically exploring, you check out all possible solutions to the problem at the same time, and you arrange it so that the right one is enhanced by an interference between paths that makes it stand out. But the classical, the problem, the frustrated magnet. Well, okay, I'm thinking about the usual frustrated magnetism problem. Frustrated magnets, quantum mechanically, frustration can lead to interesting kind of spin liquid states, but those are not really due to randomness. But you can. Yeah, you could make there's other kinds of frustrated magnet models, or models with frustration can give rise to interesting topological states too, right? But I think the usual frustration problem in magnetism is this one of the classical magnet, where there's lots of different possible arrangements that almost minimize the energy, and you have to find out which one it is, and does it have a memory effect? You think of it as a landscape with lots of minima in it, and you can get trapped in one minima and things. So I guess the answer is it's the usual classical frustration magnet thing is not a quantum problem.
All right, many thanks for the answer. There are so many questions from the audience, I must say, and actually at the peak we had circa 300 people watching us. So would you mind answering a few more questions?
Sure, I have no problem.
Yeah. Okay, so there is actually one relating to what you said. So are there similar topological phenomena in non-solid state systems, for example, in quantum condensates?
Well, in cold atoms in traps, right? People are trying to simulate a lot of this stuff in not in regular solids, but in solids where the atoms are held in a lattice of interfering laser beams, basically, right? So the nice thing about the atomic trap situation is that the in solids materials, you've got all these lattice vibrations and phonons around and stuff like that, and imperfections. You can actually make a much more toy model kind of solid using cold atoms in atomic traps, because the lattice in which they're held is not due to themselves. It's actually due to the interference pattern of 2 or 3 or more laser beams to give you kind of regions of high and low optical intensity, which provides which will trap atoms want to go to regions of bright regions because they're diamagnetic, right? So condensates become solids. Now liquids that people want to try and basically one of the rationales for cold atoms in traps is one of the things that people hope to do is basically simulate all these kind of theorist models from condensed matter in cold atom things, and in fact, because of the atoms have so much more possible variability. I mean, you can get all kinds of things. Instead of spin a half, you can get groups, SUN groups with calcium atoms, because they have the nuclear spins have a large degeneracy and stuff. So there's lots of interesting things you can do with them, but they're not really liquid states. The interesting things are with the atoms in traps, which makes them into solids again, or at least liquid-like states of atoms with a solid background.
All right, thank you. We have another conceptual question. Could you explain simply the difference of how non-topological and topological entanglement is physically created?
Well, I guess it's not that entanglement is topology. The entanglement, the interesting states, their entanglement has some kind of interesting topology. It can be classified. There's something you can call the entanglement spectrum. You can kind of so if I cut the system in half, I can try to stitch it together, right? If it's a product state, there's a single, it's just a direct product. That's a single level. You can actually study how something is glued together. I guess a bit like in this picture here, right? If you take this state and you try to examine an expansion of the system as a product in products of states at the left and right, with this kind of coupling between the two, you can actually see some interesting topology. You can see topological aspects of the way the two systems are combined, and that's topology. So the it's not such a thing as non-topological and topological entanglement. It's really that the entanglement has a topological. If the entanglement has a topological property in it that essentially means it essentially means if I chop the thing in half, the way the two sides of the system are stitched together, which is Schmidt entanglement, right? Bipartite entanglement has a topological character to it. Yeah. So I'm not quite sure what to say otherwise.
All right. So we have one last physics question, and this will be rephrasing. Does the conductivity on the edge of a topological insulator show any exotic behavior like superconductivity?
Well, superconductivity is probably an alternative possible. Well, on the surface of topological insulators, you have you can get you can also get topological superconductors, of course. Probably that's what the classification of topological bands has gone into topological superconductivity, and basically the Kitaev chain. Topological superconductivity generally comes about when you're not coupling pairs, where the electrons are not spin up, spin down pairs, but actually electrons of one particular type. Like if you couple electrons of the same spin together to form a pair, when you've got that, you actually can end up with these half electron states in Majorana zero mode. So yeah, people have basically been looking for the combination of topological insulators and putting superconductors. So mixing these things up, finding boundaries between superconductors and topological insulators, or putting superconducting layers on the surface of topological insulators, just like putting magnetic layers on them, is one of the ways people are looking to find more exotic things.
All right, thank you. So there are two questions which I will merge to one, which are more related to life advice, actually, for physicists. Okay. So one question is quite specific. What books, literature would you recommend for a beginner in this topic, topological materials? And the second one is what advice would you give to aspiring physicists?
Okay, a book, I don't know. I'm not sure. There's various books come out. I know Bernavig wrote one, but I don't have any books to endorse, really. The problem is I haven't read the books. I would say, but, you know, there's some various books. If you just Google, I'm sure you'll find interesting books, right? So the life advice, what was the life advice? Or advice for a physicist? Well, interesting question. I mean, you know, most, you know, you might ask, why do you study physics, right? Well, most people who study science or in general, or physics, they come in with a dream. You know, they're inspired by, you know, tales of Einstein or some programs they saw on TV when they were a kid or whatever, or teacher. Usually the inspiration comes from some kind of particularly dedicated science teacher in school is often the source. In fact, when I talk to people who succeeded in different branches of sciences, they usually have some kind of story about school. But, you know, you go into this thing and you actually don't know where it'll take you, really, because you're not capable of, you know, you could just find something intensely interesting, right? But to choose which path to take in physics, you basically have to take advantage of whatever there is, wherever you're studying it, right? I think if you can find a kind of a mentor who will kind of inspire you in some way, that's the most important thing, I think, in helping you to develop a career. You need to get excited. And on the other hand, you know, not everyone who goes into, you know, studying research level physics is going to end up as a professor, right? So you don't know where you're, but the nice thing about studying physics is it teaches you to think. I think the main issue in science is not to find the answer to the problem, but to find the right question to ask, right? Because science is not like a homework problem where someone who wrote the problem kind of knows how it should be done and knows what the answer is, right? So basically the big issue is you don't actually know what the question is, and so you're groping around to find the right question, and that training and of doing that, I think it is very valuable because it gives you the tools. You know, maybe you have to go out and join a bank or something like that, right? I mean, I don't know, but it gives you the tools to have quantitative analysis that can be useful in all kinds of professions. So, but you have to follow your dream in science, right? Because the only thing that makes it worthwhile is your passion. You need passion to drive you forward. You can't, but on the other hand, you can't predict you're going to discover something great, and your career sort of depends on things outside your control. When I started, I was at Cambridge. I decided to stay on at Cambridge, and I applied to stay on for graduate work. And the two choices, and I went to a class that on advanced quantum mechanics that was split between Phil Anderson and Mike Green, and they each taught half a semester or half a term of this thing. Mike Green did Dirac equation, and Phil Anderson did localization type ideas. so I was excited by both of these things, and I had the opportunity to either work with either of these two guys when I got admitted. And the issue was I could have, if I'd chosen, Mike Green had told me about non-relativistic rotating strings, which was early string model for string theory for the hadrons, right? It was kind of interesting and challenging. And Phil Anderson had the thing about magnetic impurities and stuff. And in the end, I decided it was more concrete to work on condensed matter, right? Because I could have chosen to work on string theory, but this was before string theory. This string theory went away for a long wilderness period soon after that, when it became clear that it was not a theory of the hadrons, right? So you make some choice, and all you can do is you make random choices. Basically, you can just go with your gut feeling, and if it works out, you know, you can end up in you can stay in this research pyramid, but the main thing is that you follow your dream as far as you can. And but the nice thing about quantitative physics training is that it makes you can do useful things using quantitative thinking for other problems useful for society too.
All right, thank you. Thank you so much for the whole Q&A. And on behalf of our audience, let me thank again for answering all of the questions. It was a great honor to hear your talk at our society. Now let me just announce two things. So actually, regarding quantum computing, we have a talk on the 1st of November by Dr. Abhinav Kandala from IBM Research. He's an experimental physicist working on superconducting qubits. So the talk will start at 7 next week. And also, like the another event that I already mentioned, we have a careers conference on the 31st of October, starting from 9 a.m. And finishing at 7 p.m. There will be actually talks on academic reality by Professor Mike Payne from TCM, Chair of Computational Physics, and Dr. Tina Porter, reader in high energy physics here in Cambridge. We'll have some fireside chats with our sponsors regarding machine learning, innovative products engineering, STEM consulting, and quantum computing in the companies. And of course, there will be some students sharing academic research internships experiences, and there will be a session by Cavendish, Inspiring Women by women leaders in STEM subjects. All right. So Professor Harding, thank you so much for a great talk, and hope to see you at some point in Cambridge. Let us know if you come in the nearest future to Cambridge. So we'll definitely be very keen to offer you a dinner and meet you in person, if of course the pandemic situation will
COVID permitting.
COVID permitting. Many thanks again. Great pleasure.
Bye. Thanks for inviting me. It's been a pleasure.
You're more than welcome. Thank you so much. All right. So at this point, we might end the session, I think. Thanks a lot.